Hold up your hand. Right now. Look at the back of it, the skin, the veins under it, the little ridges of your knuckles. Inside that hand, there are electrons. A lot of them. Roughly 10,000 trillion of them, give or take. A number so large that writing it out is pointless, because your brain rounds every number past a few thousand down to the single concept of a lot. So don't try to picture the quantity. Picture just one. One electron, somewhere in the tip of your index finger. Now here is a question that sounds like it should have a boring textbook answer, and does not. It has no accepted answer at all. How does that electron know exactly how much to weigh? Because it weighs exactly the same as every other one. Every electron in your hand. Every electron in this room. Every electron in the sun. Every electron inside a star in a galaxy 11 billion light-years away, whose light left before the Earth existed. All of them identical. The same mass. The same electric charge. The same spin. Not roughly the same. Not the same to within a reasonable tolerance. The same to more decimal places than we have ever been able to measure. And we have measured this thing to a precision that is frankly obscene. And I want you to sit with how strange that is, because nobody ever tells you to. No two snowflakes are alike. No two grains of sand on any beach on Earth are identical. No two anything are identical. Not two apples, not two cells in your own body. Not two stars, not two atoms of gold, if you look closely enough. Nature does not make perfect copies. Nature is sloppy. Nature is a craftsman who eyeballs it. Every single object you have ever seen or touched or been is a one-off, slightly different from every other object of its kind. Except the electron. The electron is flawless. The electron is mass-produced to a tolerance of 0 by a factory that does not exist, out of a blueprint no one has ever found. So, why? Why the electrons? In the spring of 1940, a young graduate student at Princeton picked up a ringing telephone. The student was Richard Feynman. Not yet famous, not yet the man who would help build the atomic bomb, not yet the physicist half the world would come to adore. Just a sharp kid on the end of a phone line. And the voice on the other end belonged to one of the most respected physicists alive, a man named John Wheeler. Wheeler didn't say hello. He didn't ask how the work was going. He just said, "Feynman, I know why all electrons have the same charge and the same mass." And Feynman, reasonably, asked why. And Wheeler said, "Because they are all the same electron." This video is about the idea that came out of that sentence. It is, I think, one of the loneliest thoughts a human being has ever had. And by the end, I want to have earned that word, lonely, because it is going to mean something very specific and very heavy. The idea is almost certainly wrong. Feynman knew it was probably wrong. Wheeler knew it too. And yet, the strangest part of this whole story is not that the idea is wrong. The strangest part is which piece of it turned out to be right. Because one fragment of this unhinged phone call survived, became real physics, and quietly cracked open something we all thought was solid ground: the belief that time moves. Remember that, the crack in time. We are going to come back to it, and when we do, this stops being a video about a tiny particle and becomes a video about something much larger. Bear with me. Let me be honest about my sources up front, because that honesty is the whole point of this channel. and because this particular topic has an unusual problem. There is no book called The One-Electron Universe. There is no famous paper. This idea was never published as a theory, never written up, never defended in a journal. It exists, properly exists, in the historical record, in Feynman's own words, in exactly one place that matters: a footnote inside a speech. In 1965, Richard Feynman shared the Nobel Prize in Physics for his work on quantum electrodynamics, the theory of how light and matter actually talk to each other. And when you win a Nobel Prize, you give a lecture. Feynman's lecture was titled The Development of the Space-Time View of Quantum Electrodynamics, and it is a strange, wonderful, wandering thing. Less a formal talk than a man telling the story of how his ideas actually happened, mistakes and dead ends and all. And in the middle of it, almost in passing, he retells that phone call, word for word. Wheeler's claim, his own reply. That speech is the narrative spine of everything I am about to tell you. It is real. You can read it. And I would bet almost no one watching this ever has. The second source, the one I actually curled up with and could not put down, is a little book Feynman wrote much later, in 1985, called QED, The Strange Theory of Light and Matter. It is the best honest explanation I have ever read of how electrons and light genuinely behave. Not the cartoon version from school, the real one, the one that makes your stomach drop a little. Feynman wrote it for people with no physics background at all, and he did something rare in it. He refused to lie to make you comfortable. He keeps saying, in effect, I am not going to explain why nature does this, because nobody can. I am only going to tell you what it does, and it is absurd. And you are going to have to accept that it is absurd. I love that book. Parts of this video are basically me retelling it back to you. So that is the deal. The strangest idea in physics survives because one man mentioned it while accepting the highest honor in his field. Let's go find out what he actually said. First, we have to go back to that mystery about identicality, because I skated past it, and it deserves more. When I first learned that all electrons are identical, I nodded and moved on, the way you do. Of course they are. They're fundamental particles, right? That's just what fundamental means. But that is not an explanation. That is a word we put over the top of the mystery so we can stop looking at it. Think about what perfect identicality would actually require. Imagine you ran a factory, the best factory ever built, staffed by the most precise machines physically possible. And your job was to stamp out little metal balls that all weighed exactly the same. How close could you get? With heroic effort, insane cost, maybe you match them to 1 part in a billion, 1 part in a trillion if you're a magician. But you would never, ever get them exactly equal, because atoms are discrete and lumpy, and there is always one more atom on this ball than that one. Now here is the electron. Physicists have measured a certain magnetic property of the electron, never mind exactly what, and compared it to the theoretical prediction, and the two agree to something like 12 decimal places. 12. That is the single most precisely verified prediction in the entire history of science. It is the equivalent of measuring the distance from New York to Los Angeles and being wrong by less than the width of a human hair. And every electron gives the same answer. Every one. There is no spread. There is no factory tolerance. There is no, this one is a little heavier. You might stop me here and say, okay, fine, but so what? Maybe identical things are just allowed to exist. Maybe I'm being romantic about a non-problem. And that is a completely fair objection. So let me sharpen the knife. In everyday life, when two things are identical, we always eventually find out why. Two coins from the same mint are similar because they came from the same die. Two cells are similar because one divided into two. Sameness always has a cause. A shared origin, a shared mold, a shared blueprint. Sameness is a clue. It points backward to a common source. So when every electron in the universe is not just similar, but perfectly, exactly, flawlessly the same, what is the common source? What is the mold? Where's the blueprint that every electron in existence is reading from? Wheeler's answer was the most audacious possible answer to exactly that question. There is no blueprint being copied, he said. There is no mold. There is only one electron, and you are seeing it over and over. But before I can unpack that, I have to do something first. I have to take the electron you think you know, the tiny ball whizzing around the nucleus like a planet around the sun, and I have to destroy it. Because that electron does not exist. It never did. And this is where it starts to get strange. You were taught at some point a picture of the atom, a dense nucleus in the middle, and little electrons orbiting it in neat rings, like a tiny solar system. It's on the poster. It's the logo for 100 science brands. It is also completely, flatly wrong. And physicists have known it's wrong for about a century. Here is the thing that broke it. In the 1920s, a physicist named Werner Heisenberg proved something that still doesn't sit right in the human mind. And I don't think it's supposed to. He showed that for a particle like an electron, you cannot know both exactly where it is and exactly how it's moving. Not because your instruments are bad, not because you're not clever enough, because the two facts do not both exist at the same time. The more sharply the electron has a position, the more completely undefined its motion becomes, and vice versa. This is the uncertainty principle, and it is not a statement about our ignorance. It is a statement about reality. The information is not hidden from you. The information is not there. So the electron cannot be a little ball on a track, because a ball on a track has a definite position and a definite motion at every instant, and the electron is forbidden from having both. So what is it then? The honest answer, and Feynman insists on this in his book, is that the electron is a cloud. Not a ball inside a cloud, not a ball we've smeared out because we can't see it well. The electron, when it is inside an atom and no one is looking at it, is genuinely spread out into a haze of possibility that fills the space around the nucleus. It is, in a real sense, everywhere in that region at once, and nowhere in particular. There is a place it's more likely to be found, and places it's less likely to be found, and that pattern of likelihood, that cloud, is the electron. That is the actual object. Let me make that concrete, because abstract is easy to nod along to, and hard to actually feel. Imagine a fan, an ordinary desk fan, with a single blade. When it's off, you see one blade, one solid object in one place. Now switch it on and spin it up to full speed. What do you see? You see a disc, a translucent gray disc where the blade is somehow everywhere in the circle at once. You know there's really only one blade, but you cannot point to it, because in any moment your eye can register, it is smeared across the whole ring. The electron cloud is like that disc, except there is no fast little blade underneath doing the smearing. The disc is the whole reality. There is no blade. The smear is the thing itself. The electron is not a fast dot that we perceive as a cloud. It is a cloud that only ever pretends to be a dot when we force it to. And that phrase, force it to, is where it gets really interesting. Because when do we ever see an electron as a dot? Only when we measure it. Only when we look. Here is the part that made physicists lose sleep for the last 100 years, and still does. That electron cloud, spread out around the nucleus, everywhere and nowhere, it stays a cloud right up until the instant something interacts with it, until something measures it. And in that instant, the cloud does something violent and instantaneous. It collapses. All that spread out haze of maybe here, maybe there, suddenly snaps down to a single definite point. The electron is suddenly somewhere. It has a location. And which location it picks, out of all the places it might have been, appears to be genuinely random. Nature seems to roll a die. Now think about what that actually means, because it is deeply, deeply weird, and physics has never fully digested it. Before you look, the electron does not have a location. Not a hidden one, not one you don't happen to know. It does not have one, the way a cloud does not have an edge until you decide where to draw the line. And then you look, and the act of looking is what gives it one. The universe, at the smallest scale, appears to be sitting in a kind of shimmering indecision, a fog of every possibility at once, and it only commits to a single sharp answer at the exact moment it is asked a question. It is almost as if the universe is waiting to be observed before it bothers to decide what's real. Sounds like nonsense, I know. It sounded like nonsense to Einstein, who hated it, who spent the last decades of his life trying to prove it couldn't be true, and lost. This is the real thing. This is not a metaphor. The best tested framework in all of science says that the smallest pieces of you do not have definite properties until they are measured. I have circled this measurement problem before on this channel, and every time I come back to it, I understand it a little less, which I've decided is the correct direction to be moving. So, let's assemble what we've got. The electron is not a ball. It's a cloud of pure possibility, everywhere at once, that becomes a single point only when observed. And there are, supposedly, an unthinkable number of these clouds, and every single one of them is a perfect, identical copy of every other, for a reason no one has explained. That was the state of the mystery when John Wheeler picked up the phone. And what Wheeler proposed was to take one absurd idea, the electron that's everywhere at once, and push it to its most extreme possible conclusion. Here is what Wheeler actually meant. It's simpler than it sounds, and much stranger. To follow it, you have to stop thinking of an electron as a thing that exists at a moment, and start thinking of it as a thing that exists across all of time at once, as a line. Picture it like this. An electron is born somewhere, moves around for a while, and eventually is destroyed somewhere. If you drew its position at every instant of its life and connected the dots, you'd get a line snaking through space. Physicists call this a world line, the complete trace of a particle's entire existence laid out as a single thread. Not the particle at one moment, the whole life of the particle, drawn out end to end, like the trail left behind a slow exposure photograph of a firefly in the dark. Now, Wheeler's idea. Take one electron, just one, and let its world line be insanely, cosmically long and tangled. Let it be born at the beginning of the universe, travel forward in time for a while, then turn around and travel backward in time, then turn around again and go forward. Over and over, billions upon billions of times, zigzagging up and down through the entire history of the cosmos, threading through every atom that will ever exist, before finally ending at the very end of time. One thread, woven back and forth through the whole fabric of space-time, uncountably many times. Now here's the payoff, and it is genuinely beautiful. Here's how one thread makes a universe full of electrons. Imagine that whole tangled thread, the entire back and forth life of the one electron, as a single strand of string crumpled into a huge, chaotic ball. Now imagine a flat sheet of glass. That sheet of glass is a single instant of time, right now, this moment. And that sheet sweeps slowly through the crumpled ball of string, and everywhere the string pokes through the glass, you see a dot. How many dots do you see on the glass at any one instant? Millions, billions, 10,000 trillion if the string is tangled enough. A whole universe of separate little dots scattered across the sheet. But there is only one string. Every dot is the same string, caught at a different place in its journey. And so, Wheeler's claim, every electron you have ever seen is that single electron, caught at a different crossing point of its one impossibly long life. Your hand contains 10,000 trillion electrons, because the one electron passes through your hand 10,000 trillion times at this single instant on its endless weave through history. And now the identicality mystery, the thing we started with, just dissolves. Of course every electron has exactly the same mass and charge. Of course they're flawless copies. They were never copies at all. There is nothing to copy. There is one object, and you are seeing it from 10,000 trillion angles at once. And naturally, it looks the same each time, because it is the same. The mystery of the perfect factory vanishes, because there is no factory. There is one electron, and it is everything. That is the one-electron universe. And when I first really understood it, I had to put the book down and stare at the wall for a while. Because as an answer to why are they all identical, it is perfect. It is the only answer I've ever heard that actually explains the perfection, instead of just naming it. There's only one problem, and Feynman spotted it in about 4 seconds, right there on the phone. Here's the objection Feynman raised. It's a good one. But to understand it, I need to hand you the single most beautiful piece of this whole story. The piece that survived. The piece that turned out to be true. Go back to the thread zigzagging through time. Forward, then backward, then forward again. Now ask a simple question. What does it look like to us when the thread is running backward? We can't run backward through time. We are stuck moving one direction. Forward, always forward, into the next second, never the last one. So when the one electron turns around and starts moving backward through time, we can't perceive it as backward. We're not built to. Instead, we perceive that backward running segment as something moving forward, but with everything flipped. A backward-in-time electron looks to us exactly like a forward-in-time particle with the opposite electric charge. And here's the thing. That particle, same mass as the electron, opposite charge, is not hypothetical. It is real. We have made it in laboratories. We have photographed its tracks. It's called the positron. It is antimatter. When an electron meets a positron, they annihilate each other in a flash of pure light and simply cease to exist. The positron was predicted in the late 1920s by a physicist named Paul Dirac, whose equations demanded it before anyone had ever seen one, and it was found in 1932 by Carl Anderson, exactly where the math said it would be. Antimatter is one of the most solidly established facts in physics. and Wheeler's idea gave it a jaw-dropping new meaning. In this picture, antimatter is not a separate kind of stuff. A positron is just an electron moving backward through time. Matter and antimatter are the same thing, seen running in opposite temporal directions. The annihilation flash, when an electron meets a positron, that's not two particles destroying each other. That's a single electron reaching a corner in its world line, reaching the top of a zigzag, the point where it stops going forward and turns to go backward. There's no destruction at all. There's just a U-turn in time, and we, trapped watching from the outside, see the arrival and the departure as a collision, a birth and a death, when really it's one continuous thread bending back on itself. I need you to notice what just happened, because it's easy to let it slide by. I just told you that the difference between matter and antimatter, one of the deepest divisions in all of physics, might be nothing more than the difference between forward and backward in time. That a particle and its antiparticle are the same object, filmed in opposite directions. And if an idea like that, a particle running backward through time, wearing a disguise we call antimatter, is the kind of thing that lodges itself in your skull and refuses to leave, then subscribing to this channel is probably a wise move. Not because I need the number to go up, but because where we're going in the next few minutes is stranger than the antimatter. The antimatter was the warm-up. What comes next is about whether time moves at all. Stick with me, because now, finally, Feynman's objection. Feynman listened to all of this on the phone, and he said, more or less, "Professor, that's beautiful, but it can't be right. If every backward segment of the thread is a positron, then the universe should contain exactly as many positrons as electrons. One U-turn up for every U-turn down. One bit of antimatter for every bit of matter." But it doesn't. Look around. The universe is made almost entirely of matter. Positrons are rare. Antimatter is vanishingly scarce. So where are all the positrons your one electron is supposed to produce? And Wheeler, and I love this, Wheeler basically shrugged. Well, he said, maybe they're hidden. Maybe they're tucked away inside the protons, or somewhere we haven't looked. It's a hand wave. Everyone knew it was a hand wave, including Wheeler. And that hand wave is where the one-electron universe, as a literal theory of everything, quietly dies. The missing antimatter kills it. As a cosmology, as a claim that there is genuinely, literally only one electron, it does not survive contact with the actual universe. So that's it, right? Fun idea. Beautiful idea. Wrong idea. Roll credits. No, because this is the moment the whole thing turns, and everything I've told you so far rearranges itself into a different shape. Here is what I didn't emphasize. When Feynman hung up that phone, he did not throw the whole idea away. He kept the good part. He threw out the cosmology, the one electron being all electrons part. But he kept the mechanism. He kept the idea that a positron is an electron moving backward in time. And he built that single fragment into a working piece of physics, a way of drawing and calculating what particles actually do, in which particles routinely run backward through time as a normal, computable part of the process. Those drawings are called Feynman diagrams. Physicists use them every single day. They are not philosophy. They are not speculation. They are the standard tool for predicting the outcomes of particle experiments. and their predictions are confirmed to that same absurd precision I mentioned at the very start. The 12 decimal places. That agreement comes out of exactly this machinery. That is the piece that won the Nobel Prize. That is the fragment of Wheeler's crazy phone call that turned out to be real. Not the one electron, the backward electron. And I want you to feel the weight of what that means, because it's the reason this video exists. If the equations of physics work, if they make correct predictions, while treating a particle as moving backward through time, then the direction of time is not built into the particle. The electron does not carry an arrow. The physics does not care which way time is flowing. Forward and backward are equally valid, equally computable, equally real to the electron. The distinction between past and future, the thing that feels more certain to you than anything else in your entire life, appears to be something the fundamental equations simply do not contain. Let that sit for a second. You have spent this whole video thinking you were watching something about a tiny particle, about electrons and clouds and antimatter. You weren't. That was the misdirection. This was never a video about electrons. It's a video about time. Because the one-electron universe forced us to look directly at something we normally never question. The idea that time flows, that the past is gone, and the future isn't here yet, and we are riding the knife edge of now from one to the other. That feeling is the most basic fact of being alive, and the physics, the real, working, Nobel-winning physics, just quietly told us that the particles we're made of don't seem to know about it. So let's follow that all the way down, because it goes somewhere unsettling. If the fundamental laws don't distinguish past from future, if a particle can run either way, then physicists have to ask a question that sounds insane until you realize they mean it completely seriously. Does time actually flow at all? Or is the flow an illusion? Something that happens in us, not in the universe? There's a picture of reality that comes out of this, and it comes out of Einstein too, from relativity, from a completely different direction, which is always a good sign when two separate roads lead to the same strange place. It's called the block universe, and here is what it says. It says the past, the present, and the future all exist, equally, right now. It says that time is not a moving spotlight that shines on one moment and then the next, lighting up nows one after another. It says time is more like space. Just as every place exists at once, New York exists while you're standing in Tokyo, you're just not there. Every moment exists at once. The moment of your birth still exists. The moment of your death already exists. They are all just there, sitting at different addresses along the time direction. No more coming into being or passing away than the city of Paris comes into being when you arrive and passes away when you leave. In the block universe, the entire history of everything, the Big Bang, this moment, the last star burning out trillions of years from now, is a single, finished, four-dimensional object. Complete, static, already whole. And the flow of time, the feeling of one moment giving way to the next, is not a feature of that object. It's a feature of how a conscious creature, threaded through it, experiences it from the inside. Like frames of a film that already exists in full on the reel, experienced as motion only because you're running through them. Let me give you the thought experiment that makes this land in the body. Think of a loaf of bread. The whole loaf is the universe, all of space for all of time. Now imagine slicing it. Each thin slice is a single moment, a single now, all of space at one instant. You experience life as one slice at a time, in order, and it feels like the slices are being created fresh as you reach them. But the loaf was always whole. Every slice already existed, sitting there in the bread, before your knife ever arrived. You're not creating the moments by living them. You're just cutting through a loaf that was already, entirely, there. And now, here is where Feynman's electron slots back in and the whole video clicks together. In the block universe, the one-electron's world line isn't a story that unfolds. It's a single, finished, static thread laid out complete inside the four-dimensional loaf, from the beginning of time to the end of it, zigzagging through every instant at once. The electron does not experience a now. It has no present moment. Its whole life, every crossing point, every U-turn, every atom it will ever pass through, exists all at once, seen whole, from outside of time. The thread doesn't move. We move along it. Or rather, we feel like we move, and the electron doesn't even get that consolation. And there it is. That's the crack I promised you at the very beginning. The one-electron universe is dead as a cosmology. But it left this behind, a working, tested hint that the arrow of time is not fundamental, that the flowing river of past into future might be a thing that happens inside us and nowhere else, and that the universe itself might be a single frozen block in which every moment you have ever lived or will ever live is sitting right now, finished, permanent, and still. I told you it wasn't a video about electrons. I want to bring it all the way back down, back to your hand, because I've given you the physics, and the physics is thrilling, but there's a feeling underneath all of this that I've been circling the whole time, and I owe it to you to say it plainly. Suppose, just for a moment, that Wheeler had been right. Suppose the missing antimatter turned up somewhere, the objection dissolved, and it really was true. One electron, threading through everything, being everything. Then think about what your hand actually is. Every electron in it, every one of those 10,000 trillion points of the same single thread, is also, at this exact instant, somewhere else. The same electron that's in the tip of your finger is, right now, burning inside a star you will never see, whose light will not reach the earth until long after you and everyone you love is gone. It's inside the body of a person you have not yet met, and now, maybe, never will. It's in the last leaf of an autumn you've already forgotten. It is the ink of these words, and the eye reading them, and the light between the two. Everything you have ever touched, every face you have ever loved, every star, all of it, the same single particle, meeting itself over and over, 10,000 trillion times, forever, and never once knowing it. Because that's the cruel part, isn't it? If everything is one electron, then that one electron is the only thing that exists. It has no companion. It has nothing to touch that is not also itself. It is, by definition, completely and permanently alone. Condemned to solitude not because it's abandoned, but because it is everything, and there is nothing left over for it to be alone with, except more of itself. That's the word I promised you at the start. Lonely. The loneliest idea in physics. Not a lonely person, not a lonely planet, a lonely universe. alone with itself because it is the only self there is. The one-electron universe is almost certainly false. Feynman knew it, Wheeler knew it. The missing positrons saw to that. But they kept a piece of it, the backward electron, the U-turn in time, because that piece was true, and it left a crack in something we all thought was solid. The simple, obvious, bone-deep certainty that time moves. So the next time you look at the back of your hand, remember that the electrons in it are perfect, identical copies, for a reason no one has ever explained. And remember that at least one serious physicist believed the reason is that they are not copies at all. That you are holding the same single, lonely thing that is, at this exact instant, burning inside a star you will never see, and waiting inside the body of a person you have not yet met. One electron, everywhere, forever, and completely alone.